Hello, everybody. Hello, everybody in the room here at the Center for Demographic Studies. And hello also everybody who is joining online and who are attending these two sessions on this training on machine learning tools for the analysis of migration trajectories. So I'm just going to introduce myself. My name is Sergi Vidal, and I'm an associate professor at the Department of Sociology at the Universitat Autònoma de Barcelona. And I'm also a senior researcher here at the Center for Demographic Studies. So I will be leading this session today, where I'm offering you a concise introduction to sequence analysis with a particular focus on the description of the identification of patterns in residential mobility or migration trajectories. So I want to, the structure of these sessions is about 2 hours, each of them, and there will be like a 5 minutes break. It's more or less like a 1 hour and then 5 minutes break, but I cannot tell. It depends on about how much cover. We're going to be more or less in the middle. And I want to clarify 2 additional things about the sessions. One of them is about intervention. Those who are here in the room, you can ask anytime, especially for clarifications. Those of you who are online, I cannot see you and I cannot hear you, but you can engage with me through questions in the chat. And at the specific points of the session, I'm just going to make a break and let Ricardo Valente, who is assisting us here today, so to tell me a selection of questions, because it depends on how many questions you put. I might not be able throughout this session to answer all of them, but I will try to do my best. The second thing I wanted to mention, it's about the course materials. I already sent you in an email yesterday, the materials. The materials are basically these handouts that now you can see on the screen. There's also the data that I'm using for exemplification. And you have also an R script. So this is basically statistical code to replicate all the output that I will be showing you throughout the session. So if you've got the computer on you and you open R and you upload the R script, you might be able to run the script as I am doing it. All right. So I think that this is basically everything I wanted to say about the structure. And before we move in, we move on with the index of contents of this session, I just want to acknowledge the sponsor of this session. This workshop or this training is sponsored by the International Union for the Scientific Study of Population, and more concretely by the Panel on Lifetime Migration. This is a scientific panel with a 2 years duration, starting this year in 2023 and lasting until 2025. And our aim here is basically these 3 objectives. First of all, is recognize the heterogeneity of migration's behavior in individuals' lives. So understanding migration as a wider part of individuals' lives, as trajectories, so that we understand or we move beyond this typical examination of migration, comparing movers and stayers, or before and after migration, and considering that migration can be something that it's repeated, can be chronic, can be circular. So they are very diverse and heterogeneous patterns. Relating to that, one of the other objectives is to integrate research on internal and international migration, and basically throughout the lives of people, understanding that when we talk about migrants, they also have a past. They're moving across other countries, but across other regions in origin and destination countries. And this speaks quite a lot about the diversity of these groups. We cannot talk about movers being in homogeneous groups or stayers at the point in time being in homogeneous groups. And finally, related to that, to this understanding of mobility as trajectories, as diverse trajectories, we want also to establish how migration trajectories underlie individual and societal well-being. So trying to understand the outcomes of migration, not comparing movers and stayers, but also looking into different types of profiles. So if you want to know more about the panel, you just have to check on our website. And in our website, you will see that we will be hanging more information about scientific meetings that we plan to organize, as part of conferences. For instance, this year in the British Society of Population Studies conference, we have 2 sessions on childhood migration and also on migration trajectories over the life course. Next year, just before the European Population Conference, we are organizing a scientific workshop, also with master classes, also to learn methods. We are also organizing webinars. So for instance, in the fall, we will have a webinar about data infrastructure to analyze international migration trajectories. So following international migrants across countries and so on. There is a number of interesting events that you just can check in this website here. All right, so now we move on with the contents of the session today. So I have to be honest, this is only a 2-hour session. So that means that I cannot really cover all the potential that has the sequence analysis toolbox. And that means that I will just focus on what we know the core of the sequence analysis toolbox, just the rudiments, just how sequence analysis is known since the very beginning in social science back in the 90s. So my idea to cover these notions is, first of all, the idea or the notion of what is migration as a trajectory and how can we empirically operationalize and analyze this as sequence data. Then we will move to a more applied thing that we'll see once we have these migration trajectories and we have some data on that. How can we handle this sequence data, these migration trajectories in the R environment? So in a statistical software, which is very flexible and it's very useful to analyze trajectories. Then we will move on to representing and summarizing the sequence data. Basically, these are basic and simple descriptions. They are not very complex. We will not use notation here. I just prefer to tell you the intuition and to show you how can we generate output these descriptions using the R software. And we will focus here on visualizations because sequence data is categorical data. It's very complex to describe and summarize just using means or averages and so on. So we will use visualization because we want to focus here on measures of heterogeneity and diversity and looking into different patterns. So the last step will be the identification of patterns in the sequence data. And here, basically, we want to look with a method which is a little bit more complex, that we have this very complex set of data. And of this complex set of data, we want to observe some patterns. We want to see how people is migrating in different ways. So what different migration trajectories we have. And for that, what we will do is follow 2 steps. First of all, we will compare our sequence data. We will compare the sequences of different individuals, their trajectories. And once we have compared and we know how similar or dissimilar they are to each other, we will group them. We will put them into groups according to their similarity. So for the first step, we will use optimal matching, which is a sequence comparison method. And for the clustering, for the grouping of the data into groups, into patterns to generate this typology, we will use cluster analysis. Cluster analysis will use the output of optimal matching to cluster sequences into groups that are very homogeneous across them. So let's start. Okay, we'll start with the notion of migration as a trajectory. And for that, I just want to put you a couple of examples of how can we understand migration as a trajectory based on research or a couple of research papers out there that are very clear and very useful. So the first example I want to talk about is migration being not a one-off event, but migration being something that you can repeat over the life course. And for that, I will use this paper for exemplification of Aude Bernard, where she asked the question of how often and what patterns of repeat migration can we observe across migrants. So for that, she uses retrospective data, retrospective survey data. So asking a cohort of older people about their past life. So she collects, or this data collects information about all the places of residence of people since birth until age 50 or until age of the interview. Okay, and then what she is using for the analysis is all these migration records from birth to age 50 for these cohorts born between 46 and 64, 1946 and 64, in 27 European countries. Okay, and she's got information of each move relating to two aspects, two dimensions of the movement itself. One is the frequency, and the other is the direction. So frequency being first, second, third move, and direction being onward move, so leaving a region that you were living before, and return move, so return to a region or to a country that you lived before. So she ended up with these different potential migration states. Here you can see, so at the very beginning, before a move, we are in a state that you have not moved yet. Then after your first move, you are in a state that you did an onward move to a new area. Then people can return to the area that they left. That would be the first return move. They could move forward again, so to a third area that they haven't lived before. And then again, second return move, third onward move, return move, and so on. So the results of her analysis basically is to try to illustrate how migrants basically do not move only once. And she generates this typology where she basically finds that these were the most common trajectory pathways, basically being the pathway of one-time migrant between birth and age 50, only the case of 48% of those who's got migration experience. So this is basically the percentages refers to people who's got migration experience, migrants, between age 0 and age 50. 48% means that this is less than half of all migrants, meaning that the majority of migrants have actually moved more than once. And not only move only a second time, there are diversity. There are diverse ways they move. So we find that 30% they did a move onward and a return migration. But we have also that 12% they did not return. They did several onward moves. So move from an area to a second area to a third area, and possibly more areas, because here the data is censored to the third onward move. And finally, we have also another typical pattern, which is circular migration, people moving forth, back and forth to areas that they have lived before. So the conclusion here is basically that understanding migrants observed at the point in time as a homogeneous group probably is masking some kind of diversity that might be relevant to understand their behaviors, their outcomes, and many other things. All right, so this is one example. Another example here, it's now on migrants' administrative status. Now we do not focus on the entire trajectory of migrants since birth. Now we focus on the trajectory of a migrant when he arrives to a country, and then in what administrative status it has this migrant over the course of his life in this new country, right? This is a work by Schumacher and colleagues from Belgium, and they put this question that what are the main administrative status trajectory pathways among non-European Union migrants in Belgium? So they have here registered data. They have records of up to 6 years of migrants who arrived in Belgium, and who arrived in Belgium between 1999 and 2006, and they know the administrative state of this recent migrant each month since the arrival. Okay, so which kind of administrative states we can find here? So a migrant can have a short-term permit, which lasts between 1 and 6 months, and this is something that you get where you are waiting for a different type of permit. Then you can have a temporary permit, which normally lasts between 1 and 5 years. They can have also a permanent residence. that normally requires to have shown like a residence time of at least 5 years or something like that. Then they can become Belgian citizens at some point of time. They can end up in a irregular status, so basically no regular permit. They can emigrate when they tell to the authorities that they are just going to leave the country, but they can also be deregistered. And the register is a kind of a gray area, because they do not know whether they are in the country or that they left the country. It's after some time of their irregular status that the administration decides to deregister these people, but not knowing what has happened here. So again, what Schumacher and colleagues, they do is to try to understand the different typologies of how migrants, non-European migrants in Belgium, move through this administrative status. And they find that there are like two very common trajectories. One, it's kind of a rapid access to permanent residence. So a migrant could be 6 months in a short-term permit, then between 1 and 2 years in a temporary permit, and then they become permanent. And this is about 25% of all the individuals in the registers. But then there is another very typical one, which is more kind of an irregular or like a temporal and then turning to a regular situation. So these migrants are on a short or temporary permits between 1 and 2 years, and then they become irregular because they do not have a permit. And at some point of time, after 6 months or after a year, they are registered and they do not really know what happens with them, if they are in the country or they left the country. So as you can see, we have like less than 50% following these two main trajectories. And this is because there are like a wider variety of trajectories of administrative status. Actually, they find that there is up to 5 additional typical pathways. So where I think that it's more than 5% of the migrants who follow these types of patterns, basically saying that, again, if the Belgian state should do or should understand better the needs of the migrants in Belgium, should understand a little bit much better the kind of trajectories they follow in the country. Right, so these are just basically 2 examples to exemplify to you how we can understand migration as trajectories, right? So in these previous examples, as it says here, migration or migrant status trajectories are empirically assessed with longitudinal categorical data, or what we call sequence data here. And this is the kind of data that we want to use in this course. Okay, so I mean, I'm showing you as migration, but you can think about any of the topics that you're working here in. Again, to remind the idea of a trajectory here, imagine the fictitious residential trajectory of Alex. Alex was born in a rural village R, moved to the city A, then moved abroad to the country C, and returned to the city A in the country of birth. This is the migration trajectory of Alex, which can be illustrated as a sequence here. And the sequence here, in this case, I just use these letters, but basically it shows you a number of elements or states that are concatenated. So it forms what we know sequence. RACA is the sequence that represents the migration trajectory of Alex. So just very briefly, to define sequence data, a sequence is an ordered list of elements, what we will call the calendar, which are successively chosen from a finite set of states, what we will call the alphabet or the state space, okay? So this is an example of a sequence, A, B, B, C, 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 right? So A, B, B, C, C, C has an alphabet or state space which is composed of 3 states, A, B, and C, and it has a calendar equal to 6 because it covers 6 elements And the special thing about here is like they are ordered. In this case, the dimension that orders the states is the time. Okay, we can see here from the first element, second, third, fourth, fifth, and sixth. As you can see here, we are also illustrating the sequence also with these boxes and colors. And the reason why is when we have one sequence, it's very easy just to put characters like letters. But when we're working with a million of sequences, it's better just to use visualizations, especially when we want to inspect the data. Okay, so we will be focusing quite a lot on visualizing this data, okay, and the outputs of this data. So again, the important things to define sequence data are an alphabet, okay? So the set of categorical states constitute the sequences. And in the previous examples, these alphabets were either the type of migration states, defined by the frequency or the direction of the move, or the migrant's administrative status. It's clear, right? And we need also calendar, which is a temporal order of the states in the sequence. In the first example that we have seen, these are the years since birth to age, it says 65, but I think it was 50. And then the months since arrival in the host country for the second example, okay? So these are important elements that here I just put you some example, but you need to give it a thought about what states define the process, the trajectory that you're studying, and what is the right calendar to study this process. So for those of you here, for instance, that are studying reproductive outcomes, perhaps you don't want to start studying the life of somebody at birth, because there are no possible reproductive outcomes, and you want to study a calendar that starts I don't know, at age 14 or age 16, you know, the typical age when family can start to be formed. And it lasts, let's say, at the age 45 or age 50, when the potential to make reproductive choices and so on, it starts to decline. Just to put you an example that things like alphabet and calendar, I cannot cover here right now, but you need to think a little bit about the process that you're studying to make decisions about how these alphabets and how this calendar should look like. So what I'm going to do now is I'm just going to show you the data that we're using here and tell you a little bit why we make a choice of a specific alphabet or specific calendar, right? So the data that we're using here today, it's biographies of all the residents in the city of Santiago de Chile, in Chile, of course. And this is open access data, and that's also one of the reasons why we're using it here. You can access the data just going to this link. This is provided by Ignacio Cabib from the Pontificia University of Chile. And this is a survey that was collected the data in 2019 to 802 residents. These are representative of this older population in the city of Santiago. They are all Chilean born and aged 65 to 75 in 2019, so the time of the interview. They collected residential history in the calendar format, asking in every year since birth till the time of the survey where these people was living, okay? What municipality. So we have complete residential histories of municipalities in Chile. And what we're going to do as a research objective will be to map trajectory pathways of stability and change across residential contexts and measuring residential contexts by their socioeconomic status. So municipal income distribution in 2017. So basically we will have some people who are like in poor neighborhoods or low income neighborhoods, middle income neighborhoods, high income neighborhoods. And we want to understand whether people move across type of neighborhood or they are basically stable and what diversity we can find in here. So the way we define sequences is with this calendar that we will consider the entire life, because we want to see whether people who is born in a specific type of context might keep this context over the entire life, or they might change over time. So we will have information from birth at age 1 to age 65, which is like the earliest age at the time of interview. And we will have 65 elements for each individual. Okay, this will be our calendar. And our alphabet will be composed. Here it's been a little bit for simplicity of 4 states. Okay, we will consider people in lower income, middle income, higher income, and those who come from outside the metropolitan area, they will be concentrated in a group. Okay, basically those coming from outside the metropolitan area, they don't come from high income. They normally come from lower or middle income kind of municipalities. So this is a selection of 3 sequences of our data set. We have here, just for illustration, one for a sequence going from age 1 to age 65, which is completely black. And this is basically meaning a person who's been since birth in a lower income municipality. So we could basically say that his trajectory or her trajectory is persistence in low SES context. We have another example of a person who at age 40 was also by that time in a low income context and moved to a middle income context by age 40. So we could say that this process or this trajectory, it's closer to what we would understand like an upward context mobility. And we have a last example where we have somebody who starts in a high SES, then move outside Santiago Metropolitan Area, then move back to a middle SES, back to a high SES, and by middle life, by age 30, move back to a middle SES. So, I mean, of course, we can find a name for that, but I just decided to say a complex pattern because it's not so clear as the other ones. All right. So when we see anecdotal evidence like that, it's very easy to identify the patterns. Okay, this is very clear. Persistence in low SES. This is mobility. This is complex. What happens in real life? This is the 802 sequences. Basically, this is trying to stack all the visualizations I showed you before, these bars, just trying to stack, to put them here all together. This is very difficult to understand, right? We do not see any pattern here. So the idea of the course today is try to understand and to describe this data and to see whether we can see patterns in the data. And for that, I think that one of the very useful things before describing the data as a whole, it will be to make a typology. And this is basically what I'm going to be focusing today. Because by making a typology, what I said before is like we're going to compare all these sequences across all of them. And with the result of this comparison, which is similarities across the sequences, we're going to group them. And we're going to end up, group them sequences that are similar, that are homogeneous among them. And this tells us much more about the patterns that we see in the data. So basically, the steps in the analysis of these regularities in the sequence data will be basically, first we will do an exploration of the sequences and a summarization, so some kind of a summary descriptives of the data, just to understand much better how the sequence data look like. Then we will make the sequence comparison, the sequence clustering, and then we will have this typology. And with this typology, what we can do is like describe the features of the typology. How many types we have, what kind of characteristics define, or what kind of features define these types, these different groups of sequences, and also describe the other characteristics that might be associated, like whether there is a social demographic profile behind each of these cluster types. Okay. Just very briefly, just to say that our approach to migration as a trajectory, this is alternative, but at the same time complementary to the typical approach that we use to understand migration, which is migration as an event or migration as a transition, which is what we know as a variable-based approach. And this variable-based approach follows the idea of the general linear model, where we have a dependent variable and an independent variable. I want to see the average effect of one on the other, right? So this is basically the idea of comparing migrants versus non-migrants, or comparing before and after migration, which is observed at the point in time. So our approach here, it's what it's called a process-based approach. Here we do not have a dependent variable. Okay, it follows these ideals of narrative positivism. I'm not going to enter into that, but what it acknowledges is that migration is repeated and could be part of a wider trajectory. Okay, so migration could be recursive over your life and could be reinforcing. So a previous migration could explain why you move again, or which kind of move you're doing again in your life. But what I want to say is that these are not alternative in the same of competing kind of approaches. These are complementary, because this basically, the migration as a trajectory show you the diversity of migration patterns, and it can be combined with typical methods of the variable-based approach then to explain. Okay. Okay, so very briefly, I'm not going to enter on that right now, but I have this slide where I show you different ways so that you can operationalize a migration trajectory. Okay, like you can operationalize the states regarding the characteristics of the movement, like the frequency, the time elapsed since migration, the distance of migration, direction, and so on. Also regarding context characteristics. So in this example, in this data that we're using, we are operationalizing the states based on income levels of the context of the municipalities, but you could also use household characteristics or individual characteristics to operationalize these trajectories. I've been focusing quite a lot on micro level, but you can also think about trajectories at the macro level or other levels. So for instance, we can think about following sequences or trajectories of net migration across, so for different countries or for different regions. So a region could have negative net migration, or zero net migration, or positive net migration, and the calendar could be a period here since something happened. So since the Ukrainian war started, you know, and see how it has changed the number of Ukrainians in each of the European regions or European countries. Same things with bilateral migration flows or foreign migrant stock and so on. Okay, so I'm going to take now a couple of questions from the audience, but in the meantime, I would like to you to think of your area of research and think of how can we make kind of a sequence analysis application. You know, think about your big area of research, not exactly what you're doing now, but think out of the box. Think about the overtime process, and think of a potential sequence or way to define the sequence with a calendar, with an alphabet. And it would be great if you start to think about which potential different type of trajectories you think you might observe, of typical trajectories. And you think of that? And please, Ricardo.
So far, so good on no more questions.
Any question here in the audience? All right, so let's do like yeah, please.
In defining migration patterns, you are not in explaining it using sequence analysis. You are not concerned about the factors that drive these patterns.
Well, that would be the next step, right? So right now, the only thing I'm doing is trying to see in this data, which is very messy or very complex, whether I can find some kind of a structure. But it's true that when I find a structure, meaning like a different types and so on, you might be interested in whether there are profiles, underlying profiles. So let's say people coming from specific countries more likely to follow a trajectory, or people of certain ages or gender being more likely to engage in some kind of pattern, right? So So that's part of what I would say, like once you have discovered the patterns, you need to characterize them. So explain how they are and, just, but this is just one way to identify patterns. There are also probabilistic methods to identify this type of patterns that we are not covering in this course, of course, and where you can directly input a number of variables, like social demographic variables or other types, to say, like, the pattern I want to find is not only related to the characteristics of the migration trajectory, but also of other variables of interest. So you have latent class analysis, you have mixed Markov models, hidden Markov models, and so on that you can use for that end. But we're not covering this here.
We do have a question online. If you could please give some example of multi-channel sequence analysis.
I'll do this by the very end of the session. Thank you. All right. So I think we should move on, and I should skip these 5 minutes that I said because it's already 11. I think I hope you guys are okay with moving on. All right. So this is going to be a very short part about handling sequence data in the R environment. The first thing I wanted to say is, like, why are we using R? First of all, you know that R, or you might know that R is a programming language and a software environment for statistical computing and graphics. Data analysts and statisticians are using this quite a lot, but also social scientists nowadays. But the real reason why we're using R is because it's the most flexible program or software for sequence analysis, because there's a number of packages that are specific to sequence analysis. And there are other softwares that you could use, but I don't think that they are as good as R. The other reason is because it's free. And then I can give you access to the R script and to everything. You don't have to buy a license to do the analysis in other softwares like Stata or something like that. So we're going to use the R Studio, which is this integrated development environment for R. Just very shortly, I am assuming here that people know R, okay? But for those of you at home, just very shortly, I'm just going to say that here in R, in the R Studio, you will have access, or you will see from this screen everything. So you will see the code that I'm using in this panel top left. So this is the code, and this is basically to make things happen. Okay, so I select some rows of code, and by selecting them and then clicking on I cannot see the icon, on the icon run and so on. So you make things happen. You can also do Control Enter and it's going to work. So once you make things happen, then you will see the printed output here in the console. So in this panel, bottom left. And the graphical representations, if you do any, will appear here in this panel, bottom right. And finally, any data object, vector matrix, whatever that we're creating is going to appear here in the top right panel and so on. So basically, for those who have the computer in front of you, if you don't have done that before, the first thing that you would need to do is to install the packages. But I have done that already. So what I'm going to do is, like, because the packages that we're using to run the code are already installed, I'm just going to call them. So I'm just going to open them. So I run this here. Hope it's working. Apparently it's working. So the next thing I'm going to do is just upload the data and show you the first 5 observations in my data set. So from home, now you should be seeing here that I have uploaded the data, and that I'm showing you here the first 5 lines, which rows that basically are first 5 individuals in our data set. I'm showing only 10 columns. And in the first column, you can see the identifier of the first individual, and then you can see the list of elements of the sequence. This is not yet sequence data. This is the raw data that we have introduced as columns. Okay. All right, so I'm gonna get back. Basically, there's a number of packages that we're going to use. I'm not going to enter into that. Just to tell you that the main R package that we're using for sequence analysis is called TraMiner. Okay, and this is a very wide. There's a lot of functions here. Just one thing I just want to mention here is that if you ever use TraMiner and you publish something, please mention these guys, reference these guys, because they did a lot of work and this has been for free, basically. There is a larger range of packages that we're going to use, basically TraMiner extras, wider cluster, and some others for the visualizations, which is more like kind of general packages for visualization. And you can check many of this information actually in the website here of TraMiner and also in the user guide. Okay, so one of the things just to mention for you is that I show you the data in a kind of format, but R can also read very different types of format that we can input to work with sequence data. So I show you the wide format where we have each row of data is basically an observation of individual, and then we have the information on each of the elements of the sequence as columns. But you can also have your raw data in the long format. Basically, we have one row here for each of the elements, and then we have a variable that says the number of the elements, so the order set, and then another one that tells me, in this case is X, that tells me basically the types of the kind of states. And then we can, for those who have done even history analysis, they might know this episode format also. Okay, so we have for each row represents one of the episodes in a given state with the start time and the end time in a specific state. There are a number of functions available to R to reading the data in very different text formats. But if you are working with other type of statistical software, it's very easy to input the data from SPS or Stata or SAS or whatever into R using the foreign package, okay? Any information about how to input the data from any package to R, and especially to work with sequence data, you can click here in this link that you have below. All right, so right now we just have raw data, but R doesn't know that this data should be, work as sequence data. So the most important thing we have to do when we handle the data with R is basically telling R that this is going to be sequence data. And for that, we were going to use a function that generates a sequence object out of the raw data. And for that, we use this secdef function, okay? Basically, you will have to write this line of code that I have already prepared for you, because this is the basic that you need here. You will need to just give an arbitrary name for the object. I give here set object, and I said that this is a function of the secdef, and then I mentioned here the raw data. This is the name of my data set, data one. Then I say where the elements of the sequence are stored between columns 2 and 66. Then I say, what is the alphabet? Okay, the alphabet, it's only 4 elements, so 4 different states, and they are numbered from 1 to 4. And I give some labels, short labels and long labels that we are going to use basically for the outputs, visualizations, for instance. Okay, so we can very quickly just go here to the R code, and this is the lines where we're generating our sequence data, and the result is going to be a new object here, which is called SEP-OBJ. And then we have here some of the information that we have generated. Okay, so if we write summary, this object that we have created, it tells us that, okay, we have a new sequence object. There's 802 sequences. The length or the calendar is 65. And then the alphabet is for different states. And these are their different names. So one small thing to say here is like the data will be stored in a kind of tabular form or something like that. Okay, and there are very different types of notation, but they are basically analogous. So the typical notation you will have stored the data is this state sequence data, which is the successive state of statuses. But it can be also stored as episodes. You see here, this is line here is the same as this here. So an individual is out of the metropolitan area for 2 years, then in a high income context for 7 years, and then in a middle income context for 1 year. It's just the same. It's basically different notations, okay? And then we can also skip the temporality. So just remove the number of times or years, but this is only interesting if we're interested in the order of the sequence and not the timing, okay? Okay, so is there any question, any quick question of clarification? I just wanted to go quick on that, but for you to have an idea how to prepare the data to do what it's important to us right now, which is to start with the description of the data. How does it look? Yeah.
About data preparation, if you have like multiple data sets that you have to merge it into the same data frame to work with the miner.
It depends on what you want to do. So for somebody asked before, if we work with multiple channels, basically for each individual, we have different trajectories, then that would be separated data frames and so on. But if you want to run a sequence analysis, so the description I'm going to show you and so on, it should be in one data frame. Yeah. All right. So of course, I'm not going to be able to show you all the type of description. So I just made a selection of descriptives, basically to summarize the data and to represent the data. Okay, so one of the first things that I've been already mentioning is because of the nature of the data, which is categorical, it's going to be very difficult to summarize this data with, you know, I mean, of course, we're going to generate some means, some proportions, some things like that to make like overall descriptions of the data. But when it comes to identify patterns in the data, so very different groups of individuals, it's going to be very difficult to do it with this kind of average things and so on, right? So what we're going to do is to use visualizations. Okay, because to represent the data, it's going to be more effective, especially when we have a lot of data. And the kind of graphical tools I'm going to show you are of two different kinds. One is what we call data summarization. So here we want to aggregate and summarize the information that it's stored in sequences. So basically to assess this overall heterogeneity. But we're also going to do data representation, which basically they are displays of entire sequences. And here the idea is to identify the patterns and to address within sequence heterogeneity. So where we see like the meat, the important stuff going on. So I'm just going to show you like 4 different types of data summarization and 4 different types of data representations, just for you to have an idea of how can we describe this data. Okay, I'm starting with this like overall summary of the average duration. Okay, so the mean time in each of the states. That's very interesting. So we can see here, that's the average number of years in each of the possible states, so the type of municipality. And what we observe here is that among these residents by age 65, on average, more than 30 years, are spent in a middle SES context. Almost 10 years are in a high SES context or out of the metropolitan area, and almost 15 years in a low SES context. The reason that we see a higher, so more people in middle income municipalities is because of my decision to disaggregate municipalities the income distribution was in quintiles, and the first quintile is low income, the highest quintile is high income, and the 3 middle quintiles is middle income, just to clarify this. Okay. So we can just very quickly look at this. So of course, we do not need a graph to show this, because these are basically averages, right? So I'm running here this segment T of the object, and we can see here already is telling us here at the bottom left, like the amount of years that actually is observed of people on average in these municipalities. But you can also, of course, replicate what I just showed you, which is basically this graph, and it's very easy. You can see only with one line of code, you have this information in this graph, and also with confidence intervals. Okay, so that's one. Okay, so now we know on average how long people is in each of the states. We can also wonder how many transitions is doing this population, right? Are basically stable, or are changing across these different types of municipalities. So the number of transitions here across the different states, we observe that actually only 20% of our sample did not change the type of context, meaning that stability, apparently, stability is not the typical thing, but there is a reason for that. There's people also coming outside the metropolitan area. We observed that basically 60% did change at least once or twice. So about 1 in 3 change once the type of context, and 1 in 4 change twice. And we have 20% that they are like kind of chronic movers, like changing a lot across the context. Again, you can show this information like as a printed output, but I think that always is nice to have the visualization. It's very easy. So those who are at home, or those who have here the computer, they just can run this and see basically how easy it is to generate this kind of output here. All right. So, okay, we know the number of transitions, but I think that the most interesting thing is from where people is moving to where people is moving. So the actual transitions, origin, destinations. And for that, we just can generate the transition rates, okay, across the different types of states. In this table, what you see here is in the vertical axis, what would be the state of origin, so the type of municipality of origin. And in the horizontal axis, you have here the destination. And the percentage here should be, or the proportion here should be read as the proportion of those originating in a type of context that end up in a different type of context. So those who move out, who start out of the metropolitan area, 21% will end up in a move to the low SES context, 50% of them in a middle SES context, and 29% of them in a higher SES context. So basically we have here different colors that, okay, this is a very small kind of a transition matrix, but if that would be higher, I think that the colors are very useful to tell you where are higher transitions than in others. So basically we see here that the more red is the square, basically the higher the transition rate. And we see that most transitions are going to middle SES context. And we see here especially that people from lower SES contexts, if they move, because are only those that move, they are likely to do not go to a high SES context, but to a middle SES context, so 76% of them. So again, very briefly, we just can see, we just can round the code here, and then we have this visualization. All right, so, okay. Okay. All right. So a last summary of the data I want to show you. It contains much more information than what I have shown you so far. And it's basically, it shows you the distribution of all these states, of these 4 states across all the different ages that we have. And it gives us an idea of how our population is changing across the different states over time. Okay, so what you can see here is at the very beginning of the plot, this would be the proportions of the population when they were age 0 in these 4 different states. So the proportions you can see here in the vertical axis, and we see here that up to 40% of this population came from outside the metropolitan area. And over time, especially at younger ages, by age 20, most of them, they moved to the metropolitan area. So most of these older residents, we know that they came when they were very young or younger people. And what we observe is that mostly people is ending up in this middle income type of municipality. And well, we see also some change in the low SES, not bad change in the high SES, but this gives us a lot of information here. This is the typical case where if I would show you this information in tabular format, so for each year, the proportion of people in each state, it will be very difficult to read the table. And here it's very clear that we need this kind of visualization to understand much better our sequence data. And as I said before, this is just basically summarizing overall information. So far, we haven't seen a sequence here, an entire sequence of a person. How is the life of these different persons? So this is very useful to understand how our data is organized, but it tells us very little about the patterns, about how people live their lives, how people migrate over the life course here. So that's why we have a second type of descriptions, which is what it's called a data representation, where we show entire sequences. And I'm going to show you again 4 types of visualizations to represent entire sequences. The easiest way is to use this function here, sec I plot with the lowercase I, where basically I'm just going to represent a set of sequences, not many of them. In this case, I'm just representing 10 of them, just to have an idea of how sequences look like. Okay? So basically, this is very similar to what I have shown you before in the example. I think that giving a little bit more of information, what we could do is just show again sequences, but regarding their frequency, okay, frequent sequences. And for that, we have this other function called sec_f_plot. So frequent sequences presented in horizontally stacked bars, which are ordered by the relative frequency in the data set. Here, I'm just showing the 10 most frequent sequences. These 10 more frequent sequences cover 27%, almost 1 in 3 or 3 in 10 of all sequences in our data, right? And what we can observe is that about 20% of them are 3 sequences of stability, okay? People either all the time in a middle SES context, in a low SES context, or in a high SES context. Okay, so it gives us already some information, but again, we do not see all the patterns. We just see the more general patterns. And I think that the whole idea of sequence analysis is not see the more common or average, it's just see the diversity. And for that, to see all the sequences, what we can run is, again, another plot. It's a sig-I plot with this time is the I is in a high case. And this is showing me all the sequences in our data set, okay? Problem, can we see patterns here? It's very difficult. So here there are two problems. First of all, we're supposed to be seeing here 802 sequences, so 802 lines. But honestly, I think in such a small plot, it's very difficult to print 802 lines. Basically, we have problems here. There's overplotting. If there is one color which is very dominant, it's going to be plotted over another colors. This is basically not a good representation of 802 sequences. This kind of plot, it's okay if we have up to 100 sequences. But more than 100 sequences, don't do it, because you are not going to see the actual data. So what do I recommend to do? I recommend to make a selection of sequences and plot only 100 sequences. Okay, so this is what this plot here, this representative sequences plot, which we can get with this function, is doing. Here I made out of 802 sequences, I represent them with 100 sequences, which are representative from all the other. Why are these sequences representative? They are not randomly chosen, okay? They are what we call the methoid sequence. These are sequences that cover the minimal distance to the represented sequence. So for each sequence that I'm showing here, for each representative sequence, this represent 8 sequences. Okay, 7 of them, we are not plotting them, but with the method that I'm showing in the last part of the session, you can calculate how far away are they, how similar or dissimilar they are. And I'm just plotting here this 100. And here it's much more easy to see what we want to represent, the sequences, and to see a little bit of patterns. So 2 things I want to say. One of them is that because these are only representative sequences, I'm showing here 2 indicators of the quality of the representation. An R-square, we know an R-square what it is, goes from 0 to 1. Basically, closer to 1, it would be like perfect, and closer to 0 would be like the contrary. So the R-square is 70.77, meaning that the approximation of this picture here from the reality in our data set, it's quite close, okay? The F indicator, it's also very similar. Okay? And the other thing I wanted to mention is that now we can start to see here, we can start to see like differences, right? In how people live life. We know that some people will stay always in the kind of context they were born. We know that some people came from outside the metropolitan area and moved mostly to middle income places, but we see other types of patterns, right? Okay, so we have described the data, we have represented the data, but now this is not enough to say, I guess for you, it's not enough to say what are the relevant patterns here in the data, right? And our next step is to from this data that we have here, identify different types that we have in the data. So just very 2 small things to note some this description of the data. First of all, when you have a lot of data, and especially data which is very heterogeneous, so very different people doing different things, using representative sequence is much better than trying to plot the data in other formats, like plotting all the data or just selecting random cases or something like that, because normally they will not represent your data. You will find like selective patterns that might not really represent what you have in the data. And the second other thing is that I have not focused on that, but we can also describe the data, not only comparing in the different sequences across them, but we can also generate descriptions to address the heterogeneity within the sequence. Okay, so I have no time to go into that, but you can go to papers like Richard of 2021. There is all the references I'm showing here are at the very end of this presentation slide. So you can go there, and there is a number of ways to describe these within sequence heterogeneity, which could be relating to the number of transitions within the sequence, to the number of state visits, indices of complexity that are also very useful. All right, so is there any question? Is there any question here? All right, so please. There, yeah, so in what I show you, it doesn't, because I have only calculated the transition between different states independently of when they happen. So it might happen that an individual even do several transitions of the same type, and this is going to be counted in here. So, but there are other ways. So I thought that what I show you was, you know, a way to show you a way to, you know, describe the data very interesting. But you can also generate transitions that takes into account that one person might move to the same state, for instance. And this, then the proportions that you have seen of people moving from one state to a different state would be much lower. So this would take into account the time that somebody has been in a given state. So you would have people like 98% of the time. So from those who are in a low SES context, that the next state it's also low SES context, you can find, for instance, 97% or something like that. If in the data, we would find that people in low SES context, they have no chances to leave low SES context, which is true. And we will see this later or in a few minutes, because we have only like 25 minutes.
Some of the participants did not hear very well the questions from the audience, so maybe we should.
There is a micro. Sorry, I forgot that. Yeah. All right, guys. You want me to move on? And we have 25 minutes, but I think that this is enough time to cover this last part. All right. So, okay. So now the idea is out of the sequence data that we have, we want to see patterns in the data. We want to identify patterns. And we're going to do this using the data that we have, so empirically, basically, and we were going to use algorithms, okay? Algorithms that are going to be useful to, you know, generate this typology. So again, basically to remind you where we are and what we want to do. So far we have generated sequence data, okay? And the sequence data look like that, a little bit messy. And what we're going to do is to identify patterns, is to compare all the sequences that we have in our data across them using this method called optimal matching. Okay, this is an algorithmic method. So the output of this algorithmic method is a matrix of distances. So something that actually we cannot really interpret. Okay, so we need another algorithmic method that what it does is it takes this matrix of distances and transform it in something that it's interpretable, which is a typology. And for that, what it does is it uses the information on the distances to a cluster analysis, uses the information contained in this matrix of distances to cluster the sequences into groups of similar sequences. So groups that are homogeneous. All right, so we're gonna go first very quickly on the intuition of what is optimal matching. Okay, we're just going to be focusing on the intuition. So optimal matching, what it does is aligns sequences. So it compares similarities across sequences as a whole. Okay, so it generates pairwise distances. So the distance between sequence 1 and sequence 2, sequence 1 and sequence 3, and so on and so on. And these distances represent the minimal cost in terms of edit operations for transforming one sequence into the other. So here we have sequence 1, and sequence 2. And the distance between sequence 1 and sequence 2 is how much it cost me to transform sequence 1 to make changes in sequence 1 so that it is identical to sequence 2. And for that, we have two different types of operations, edit operations that we can use. One of them is substituting one element of sequence 1 so that it's the same as sequence 2, or inserting or deleting elements in sequence 1 so that it's similar to sequence 2. So we are going to talk about subs edits and indo edits here. We're just going to see this in practice. Okay. So can anybody here in the room tell me what is the less costly set of operations to transform sequence 1 into sequence 2? And there is a cost associated to each operation that you do, okay? So if you substitute one element, it costs 1. If you insert or delete one element, it costs 1. Who can tell me here the solution? Oh, come on.
To substitute means to substitute 1 from 2 in 1.
You see sequence 1. These are the elements are the different colors. You need to substitute an element of this sequence so that it's equal to sequence 2. What would you do here?
The orange is into purple, basically.
Thank you. Basically, we need to substitute the orange elements in position 4, 5, and 6 in sequence 1 so that it's similar, equal, basically, to sequence 2, right? So the associated cost to this operation is 3. Do we see that? So we have already generated a distance here, an OM, optimal matching distance. Edit distance is also called. Okay, this was the easy one. Let's go to the next one. Okay, who can tell me what to do in this case? We have sequence 1 and sequence 2. We want to transform sequence 1 into sequence 2 by editing sequence 1. And we have here now a little change. A substitution costs 2, and one insertion costs 1, and one deletion costs 1. Okay? And we need to find the less costly set of operations to transform one sequence into the other.
It's 4 and insert 1, delete 1, 2, 3, 4.
Say that again. Delete.
1, 2, 3, 4,
Yes.
and insert the same one.
See, if I delete 1, 2, 3, 4, then it costs 4. And then if I insert, so if I delete 1, 2, 3, 4, then okay, and insert here, it's going to cost 8, right? There is a less costly way, but thank you, it was close. All right, I'm just gonna do this for you. So you were close, you were 8, but the algorithm would be better. He would have chosen 6 as a cost. And for that, the algorithm, what it did is it deleted the green element here in 1. It added the orange element here. Okay, so cost is already 2, and it substituted 3 and 4. Purple for orange, right? So you were quite close, but there was a cheapest way to do that. Okay, if we do this one by one, case by case, it's going to take ages. So what we do is just use an algorithm, okay? And for that, the Traminer package, it has this function called secdist, and this is going to do for us the computation of all these distances across all the sequences that we have, okay? And very easily here and in the R code, you will have an example of how to program this. So I use the secdist option, and then I tell this is our sequence data. Now it's not anymore our raw data, but our sequence data. The method that we're going to use is optimal matching. And in this case, I told it to use as a cost for insertion and deletion to be 1. And for substitution, I set to be 2. So if we say constant here, there are other options. The cost is gonna be 2. And I will tell you later why normally we set the indel as 1 and the substitution as 2. Yeah. But if you run this, Tramaina implements this algorithm and it computes all the distances. I mean, we just can make it shorter if you. Okay. You just can make it. You will see it happens. It's just going to be quick now here. So the result will be a matrix that you will have in the top right of your RStudio. And in this matrix, you will see that as it says here, well, it has computed the sequences and so on. And I just want to show you a little bit for you to see how these distances that has calculated, they reflect actually the differences that we see here. This is very easy because this is a very easy definition of sequence data. We have only 4 different states. So you can see here, these are the 5 first elements of the matrix of distances that we have generated. And you can see here that the diagonal is all zeros because we are comparing the same sequence, sequence 1 to sequence 1. Okay. So we see that the distance between sequence 1 and sequence 2 is going to be 46. And basically they show that the actual difference between sequence 1 and sequence 2, it's only based at the very beginning of the sequence, where the discrepancy is on the type of municipality these people was living at early ages. So let's say before age 20. But then we see that the difference between sequence 1 and sequence 3, 4, and 5 is 130. And in this case, it's the maximal distance because there is no element between sequence 1 and sequence 3 which is similar. Basically, here we have to substitute or insert or delete all the elements. Okay. So we have seen that. We have generated now this matrix of distances that we're going to use for our next step. I just want to mention a couple of things about this sequence comparison exercise that we have made right now. One of the things is that the costs that we assign to indel or substitution operations are not innocuous. It have kind of an impact on the result that we're going to get from our sequence comparison. So just to put you an example, if you put high indel costs, okay, so basically what the algorithm is going to do is mostly use substitutions. And by substitutions, by using substitutions, 2 sequences are more similar if they have the same elements at the same time. So it kind of focuses on the timing of the sequences. So things happening at the same time. These are going to be more similar sequences. So if the process you're studying, the data that you have is a structure on timing, you would be much more interested in to have high indel costs than substitution costs. Okay. If you use high substitution costs, so what the algorithm is going to do is to use mostly insertions and deletions. And insertions and deletions, basically, it means that you keep the same order. So the timing is not much important because, as you have seen, you remove the first element and you insert an element later on, right? So the timing is distorted, but 2 sequences are going to be more similar if they have the same order of states. So first one state and then another state and so on. So if you have a process like transitions to adulthood or others, that it's more important the order of the states and the timing, then you would say you should be working, with lower substitution costs. If you do not have an idea of what temporal element explain your sequences and so on, or your process, then the typical solution of what mostly people use is substitutions to indels 1. Because in this case, there is no priority in any of them. So for each substitution of an element, you need to make an insertion and a deletion. So you need to first delete an element and then insert. And this is equivalent to making a substitution. So many people that they do not care about the theoretical or, you know, some other aspects of the data, but they just want some kind of really data-driven approach to sequence analysis. They just make this choice. And many people has been making this choice, but it doesn't mean that it should be what you should be aiming at doing, because sequence analysis, and especially all these algorithmic methods to compare sequences, have been evolving quite a lot. And I would recommend you to have a look to the paper by Strude and Richard, because they offer other type of methods, including methods that are not based on alignment, but other things that I don't have time to explain here. But that there is a wide range of methods that enables you to compare sequences, and they are better or distinctive to find the similarities based on a specific aspect that you might be more interested in your sequences. Like, as I said, it could be the timing, it could be the duration in a specific state, it could be that the frequency of the change. I mean, it could be a number of things. And I think that this paper is explaining quite well. But I just wanted to give you an intuitive idea of what we're doing with sequence comparison and optimal matching here. All right. So now we have our matrix of distances, and we need to make sense out of this. So for that, we use another algorithmic method, which is cluster analysis. And cluster analysis basically is a kind of exploratory technique to group objects based on similarities. And one of these similarities could be an edit distance or an optimal matching distance that is what we have here in our matrix. So cluster analysis partitions the data. So separates the data, the sequences that we have, into groups that are as internally homogeneous as possible. So there is the minimal within group distance, and that are as different as possible from each other. So there is maximal distance across sequences in different groups, and so on. So the ideal would be that if we have calculated distance, like Euclidean distances and so on, that we can plot here and so on. So cluster analysis would take, these groups, because they are internally homogeneous and very different out of them. This is the ideal scenario when we have, data which have a real clear structure and patterns. But many times we find data like that, that the clusters that we build or the typologies that we build, they are not they do not have these very strong structures and so on. So basically, the steps to build a typology, once we have the matrix of distances, will be first to choose a clustering method. And here I facilitated for you the choice of clustering method. So typically, we use a hierarchical clustering with the word method because of the group properties that it have in generating clusters that have really good properties. I'm not going to mention here right now, but it also generates groups that are of a good size, not very small, not very large, I mean, it has a very good things. So then we will have to make the choice in the number of clusters. And once we have that, we will evaluate the quality of the clustering to see whether we have real structure we have identified real structure in the data, or we're just fishing here for patterns, right? So in R, to do the hierarchical clustering, we will use this H-classed function. And this is very easy here. You input here the matrix of distances, and you say the method that you want to use. We said that it's going to be this word method. And the result of the clustering will be this this tree. So basically now we have to make a choice here. So cluster analysis, or specifically the hierarchical clustering, is not telling us the number of groups. He's just telling us how good different sequences, different observations match each other, can be clustered together. And this is the result. So technically here we have the 800 sequences or clusters, and they are clustering according to their similarity. And then we end up here with this large group and so on. So we need to cut this tree, this dendrogram, to say, you know, what's here a good number of clusters. So basically, there are many options to make here a choice. And I would say that what we could do is to use the cluster cutoff criteria. So these are measures of cluster quality that enables to say what's the best empirical fit in our data in terms of the number of clusters. So there are a number of different measures that we could use to assess the statistical fit, to say whether it's better to have 7, 8, or 9 clusters and so on. And I don't think that there is only one measure, you know, like an R-square in regression modeling. I mean, here there are different measures that they look into different aspects of the clustering. And I would prefer to see, you know, how different measures tell me about the right, you know, what could be the optimal number of clusters to make a decision here. One of the things, perhaps to make a heads up here, is that this is only based on the data, on the empirical structure. And sometimes it might make more sense for you to have some previous ideas based on theories, if you may have, based on evidence from other research, or from some expectations that you might have about the type and numbers of clusters, because a combination of these empirical fit measures and some previous knowledge is the best way to build a typology that might be easier, so it might be better to interpret. Anyway, so as I said, there is a number of different ones, and generally I make a selection of a couple of them that they look into different aspects of the clustering. So to generate this cluster cutoff criteria to make the choice of number of clusters, we use this ask-class range function where we say here, this is the result of our hierarchical clustering. This is the dissimilarity matrix. And this is the number of different cluster solutions that we are going to be comparing. So we're going to be comparing the fit of between 2 and 15 clusters. I put here a cut of 15 clusters because generally the idea is to generate a typology of a few relevant clusters. You are not interested into generating here 50 groups, right? Especially if you have only 800 sequences. So you can print the result, but I'm just making here a graphical or a visualization of this result of the cluster cutoff criteria for you. All these things, you can write it on the script, but I'm just running now because for the sake of time. Here, I'm just showing 3 possible cluster cutoff criteria. Not going to mention all of them, but just to tell you that it's better to use 3 or some to assess discrepancies across them. So average silhouette width, Cropper Summers D, point B0 correlation. And here, these are the scores for 2. So when we would choose 2 clusters, 3, 4, until 15 clusters, okay? And then we have here the scores on the vertical axis. These are standardized scores because each of the measures have a different metric, a different range. So by standardizing, we can compare the different scores. So what we can see here is that generally, empirically, the cluster cutoff, so the best choice would be between 3 and 4 clusters. So the data is structured in a way that with 3 and 4 clusters, we would be, showing the different patterns that we see in the data. But as I said before, if you have already some knowledge about patterns that you want to see in the data, perhaps you might want to make a choice in this case, I will make a choice of 10 clusters, which is a little bit less better empirical fit, but substantively for me was much more interesting. So what I did is this choice of 10 groups, and this was basically because I wanted to show you also a little bit more of variation of patterns in our data. And the way I'm showing you the results is with these two different types of plots. So I'm showing you the state distribution plot. Again, this is the distribution of all the states at each different age, and the sequence index plot. These are the representation of entire sequences. And I'm showing you two plots because it gives you also a little bit more of information on how sequences look like, but also on how all the different states are distributed. So adding more to the description. I'm showing you here just the first 5 clusters. And basically, I just want to mention that the most typical clusters here are associated to people already living in a middle income context or moving to this context, okay? So there is not much variation about what people who started their lives in a high SES context do. They basically either stay in high SES context all the time, or some of them move to middle SES context. And I also want to show you very quickly what happens with the other 5 groups that involves people in low SES context. These are much less people, but that all these different patterns, what they show in a way or another is that those who start their lives in low SES context, or at some point of time they move to low SES context, they are very unlikely to live low SES context. There's only this very small cluster, which is only 28 out of 802. Again, this, for a paper, I wouldn't have chosen this typology. This was just to show you, okay? But what we observe here in the typology is that there is quite a lot of persistence in low SES context. So in the end, if we have to make a conclusion of this exercise, is that if I would do an analysis of this all people where they live in a context, type of context, like whether it's a high or low income context, and I just focus on the year of the survey, or the last 10 years or something like that, I would miss kind of a lot of different lives they have. And perhaps this different life they have an impact on other important outcomes, either at the individual level or at the societal level. Anyway, just very quickly, I know I'm out of time, and if this is okay, I'm just use only 5 minutes more just to give a couple more of information and to close the session. I hope this is okay also for the people who is online. Regarding about sequence clustering, so to me, a typology is useful if it talks, about the general population, and we have to think here a little bit whether the typology that we're generating is generalizable to other observations out of the sample that we're using. And that is why I told you that when you generate a typology and you focus only on the cluster cutoff criteria, then your typology will be very dependent on the data that you are using. So you have to think a little bit more theoretically whether your data is covering everybody that you want to, when of the population you want to talk about, and so on. And that is why it's important that the decision on the number of clusters is not purely based on these empirical measures, but you also think about, the general population that you want to talk about. Could be theory, could be previous evidence that we know that could be useful to generate this typology. But anyway, there is also nowadays advances for the validation of these typologies, and you can check the papers by Studer of 2018 and 2021 that shows you the results of the clustering, also with typical confidence intervals and hypothesis testing things that can be helpful also for the decision on the number of clusters. So once you have the typology, of course, what you could do is make further description of this typology using the descriptors as I've shown you before, or you could use this typology in other kind of, typical variable-based approach methods, like in regression, could be the dependent variable, could be the independent variable. I think that using the typology in this kind of context would be some kind of a descriptive approach to regression. But I think that that's one way to further describe the characteristics of the types. And once you have the matrix of distances, clustering is not the only option. With this matrix of distances, you can do other things. Yeah, there's been developments on ANOVA-like methods to study differences across groups, across different types of variables. So I mean, if discriminate important differences in the sequences and so on. There's also sequence regression trees. I don't know if you are familiar with the regression tree literature and so on, but you can also, the distances would be like kind of the input that you would give to a regression, right? And then you use other types of variables that tells you, which variables discriminate better these distances and so on. Basically, I just have been covering the core program. Okay, so this is basically how a sequence analysis in the 90s with some developments, but there's a lot of advanced topics these days, okay, such as this validation of cluster typologies, the multi-channel sequence analysis. I'm so sorry about the person who asked about the examples of multi-channel sequence analysis, but I won't have time here to take this example. Please email me. There's sequence network analysis, combining sequence analysis with network analysis. There's also probabilistic approaches to the generation of typologies that I have mentioned before, but there's also like combination of sequence analysis with stochastic modeling, with qualitative analysis, and finally, also with feature selection approaches with machine learning. And this is what Danilo will be introducing on Thursday. So guys, if you are interested into sequence analysis and you want an introduction to sequence analysis with a lot of materials to run this, I recommend you this book. It's also very intuitive, so less notation and more applied, but it gives, of course, much more information and probably much better structure than what I did today. I recommend you to go here. I mean, this book is for pay, of course, but the companion site with all the examples and all the R code is for free, and there is a lot of code. So, I mean, you don't have to do it by yourself. You just can go there, copy paste it, just change the things what you need to do. And it's very useful. This is done by Marcel Rapp and Emanuele Strufolino. Thanks that they did this great job. And if you want an overview of recent advances of sequence analysis, I recommend you this recent article by Tim Liao and colleagues, which it explains all these new things that I've been telling you. Here you have all this set of references that I've been mentioning throughout the session today. And I know it feels a bit rushed, this session today, but I hope it was just useful, at least to give you like a kind of a general idea of why we are using such an approach and why it can be useful and complementary to typical approach. In this case, with the exemplification to migration data, but it could be to other types of data. So I'm done here, and I'm open now for questions. Do you have any question from the audience?
We do have some technical questions. Basically, they ask for additional references if you might have on how to interpret clause and rewrite some part of the codes, and maybe we can share.
I'm very happy to do later on through email.
Content-wise, I would say the most relevant one is about whether all what you have been explaining might also apply for unbalanced panels.
Yeah. So of course, I just give you like I just show you here like a perfect data where we have entire information on all the elements for all my individuals. So I had for the 800 individuals information each year, but it could be possible that for some individuals I'm starting up to, or I have information for only a chunk of the sequence. And it happens many times that because of the process we're studying, imagine that we're studying like a aging process or health process where a possible outcome is death, right? So we will be observing people until some age and some other people until some other age. And if age is the variable that defines our calendar, then we will have what it's called an unbalanced data set. So longer sequences for some people and shorter sequences for some other people. There are ways to deal with that. And this is, if you're interested, I will send you the longer course on sequence analysis, where it says how to deal with this kind of data, which is not as perfect as the one I was showing here. Any more questions from the audience? So I'm gonna use this now opportunity to thank for all the people who has been attending online. Thank you for this session. We hope it was useful, and we are gonna meet back for the second session on Thursday at 10:30 for this introduction to sequence analysis with feature selection models. Thanks a lot.